Today, this is the first lecture. This is third lecture. In first lecture, we discuss essential of fluid dynamics for CFD modeling and its application. In this second lecture, we discuss basic of CFD modeling. And this is the third lecture, turbulent flow and its modeling. Turbulent flow is very important topic for CFD engineer. Most of industrial flow are turbulent in nature. Hence, its understanding is important to solve industrial problem. Turbulent flow is a chaotic flow, and its understanding is tough compared to the laminar flow. And here I presented one caricature. One person is surfing on the surface of the ocean, and he is trying to solve turbulent flow problem. There is a second person at the top of the ocean wave. He is stuck and is finding the turbulent equation. If we don't have turbulent equation, that means we never solve the complex problem of turbulent flow. That is the motive behind the presenting the caricature here. Outline of presentation. In this lecture, we discuss physics of turbulent flow, scales of turbulent flow, methods of turbulent flow investigation based on experiment and modeling. The experiment method we will discuss dual beam laser Doppler velocimetry, particle image velocimetry, hot wire anemometry. CFD of turbulent flow we will discuss after it. Reynolds Averaged Navier execution, detached Eddy simulation, large Eddy simulation, and direct numerical simulation. Then we discuss comparison of Reynolds Averaged Navier execution, large Eddy simulation, and direct numerical simulation. After that, we will discuss details of Reynolds Averaged Navier execution modeling. What are types of Ross model, like K-split, K-omega model. Then resolution of turbulent boundary layer, available of models in axis plane and open form. First, we discuss what are the features of turbulent flow. Turbulent flow, which are unsteady of periodic motion, which all velocity component, momentum, energy fluctuate with respect to space and time. Laminar flow we'll discuss here. It is a smooth flow, and then fixed pipe flow. This is pipe is fixed, and water is fall under this gravity. That we are going to learn. Turbulent flow is smoothly. Here we see the here at the surface of the ocean. We see the this surface here. We can see the fluctuation on the surface of the fluid. That means these quantities are fluctuating with respect to space and time. But here in laminar flow, this is we can see that there is a smooth variation. There is no much fluctuation. Taking another example here, from left to right, flow rate increases. Here flow rate is less. That means velocity is less. If velocity is increases slightly, then we see that their fluctuation are increasing here. If velocity is increased that too much, then we can see there is a more fluctuation at the outer surface of the fluid. That means flow is becoming more turbulent. That means turbulent is characterized with high velocity, chaotic flow, fluctuating flow, and eddies or rotating masses. These are the very important characteristic we must note. You must note turbulent flow can be decided based on the Reynolds number, which is the ratio of the inertia force to the viscous force. This is called as inertia force, and 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 the denominator we present, this is the viscous force. The ratio of inertia force to the viscous force, it is called as the Reynolds number. With the increase in inertia term, which is a highly non-linear, and it causes the disturbance in flow. When the number is greater than critical Reynolds number, then flow is called a laminar flow. If Reynolds number is greater than critical number, is called as a laminar flow. When we put dye in the color uh, or in the fluid, then we can see this type of the fluctuation. But these fluctuations are attenuated due to the viscosity, because viscous effect dampen the attenuation. When random is increases because of high velocity, the inertia force is high, and this perturbation continue to high, and flow becoming turbulent. Laminar flow is called streamline because we can see the layer of the fluid here as a smooth line flow. In turbulent flow, we can see that this perturbation. Physics of turbulent flow. Turbulent flow are highly chaotic, as we discussed. First characteristic is turbulent flow are chaotic, but this turbulent flow can be described statically. That is based on static. This fluctuating nature we can analyze. That means we can take a time average. We take a summation of the fluctuating velocity as a function of time. Then we can divide by total time. That means this turbulent flow can be understood statically. The next is the turbulent flow are dissipative. That means whatever turbulent kinetic energy is there in the flow, here turbulent kinetic energy high, but it is dissipated at the end. We see here the turbulent kinetic energy dissipated. This is the turbulent kinetic energy is there that is transferred from the mean flow energy to the this. And how turbulent kinetic energy due to a gradient in mean velocity gradient, and mean velocity flow is here, and this is the ship is there, and it is transfer energy to the mean flow, and because of their gradient in mean flow, these fluctuations are created at large level, and this energy transfer to the smallest eddies, smallest fluctuation. We see the away from here, there is a turbulent kinetic energy 0. That means turbulent kinetic energy dissipated. That is a transfer to the viscosity. It is called as viscosity. Then next characteristic is a turbulent flow, which are highly dissipative. That means there is a strong mixing of the mass momentum energy. As this mean flow passes here, but we can see there is a strong mixing of the flow because of the vortex shedding, because there's some vorticity of fluctuation. There is strong mixing. Their rotation and vorticity, turbulent flow are highly rotational. Take an example of jet flow. we take laser sheet, and then we can realize there are strong rotation. Rotation means there strong fluctuation. That means there is a presence of strong vorticity, which is a which is a never be zero. What is the vorticity is there? It is a curl of the velocity component. Even there is a curl of velocity component, that is a never be zero. You have to note that. And the level of vorticity can be observed into the smallest level. You can see the smallest level. You can see the just level of fluctuation or vorticity. Here is the, you can see the one curve jet of free jet caused by the Kelvin-Helmholtz instability. The one Corman vortex you can see the here which photo is taken for International Space Station. You can see the this vortex is observed here, here. These are the example of the natural turbulent flow. Turbulent flow, you can also note you put dye in water flow, which is over the space, over the aeroplane. Then you can note down there is a lot of fluctuation are there. But due to high velocity, this vortex of fluctuation we cannot see by naked eye. But on the right side, you can see that this fluctuation. From side view, we can see the this is the wake region, and there is a strong mixing of flow is happened. Turbulent flow can be compressible, incompressible. It can be compressible flow. When Mach number is less than 0.2, 0.3, then this flow is called incompressible. That means there is no much variation in density. If Mach number is greater than 0.3, then it's called as compressible turbulent flow. Example as a bullet going at Mach number 1.2, and this is a shock wave is there here, and this is the wake region is formed. You can see the level of the turbulence level here. Small fluctuation are observed, but this is a compressible turbulent flow. Turbulent flow and fluctuation. Turbulent can be defined as a deterministic chaos. Turbulent flow is chaotic, but statistically can analyze. When non-stationary part du by dt is non-zero, this is the velocity. This is the velocity is there, and this is the time is there. You plot here, then you can see this fluctuation. And take average is, this is called velocity average. And when this velocity is non-zero, is called as a non-stationary turbulent. In turbulent flow, velocity scalar vector all quantity varies with space and time. And this is the average flow. This is the V bar is average flow, and this is a fluctuating component. When there is a fluctuation above and below, is called a fluctuating quantity. That means instantaneous quantity is equal to the average quantity plus fluctuating quantity. This average quantity is obtained from this one, and fluctuating quantity is obtained is fluctuation above below of the average value. Any instantaneous quantity is equal to the sum of the mean or average value or and a fluctuating value. Turbulent kinetic energy is equal to the turbulent kinetic energy is equal to the Sum of the total energy purchased by the all the EDs. For each ED, we can find out the thermokinetic energy. We can write thermokinetic energy as a wave number. We integrate over it, then we get total kinetic energy of fluctuating eddy. It is also called thermokinetic energy. Then large energetic eddies can break into the smaller eddies. This is large eddy is there, and it break into the intermediate eddy. Then again it breaks into the smaller eddy, and this is called as smallest eddy. This is called as the smallest eddy. This is called as the Kolmogorov eddies. This is the smallest eddy, which is called as the Kolmogorov eddy, and which has random number is equal to 1. It cascade energy passes through from the smallest larger eddy to smaller eddy, then smallest eddy to the viscosity. And for smallest eddy, the energy thermokinetic energy converted to friction. And here thermokinetic energy is presented on the y-axis, and the wave number kappa is presented on the x-axis, and it is equal to order of reciprocal of the size of eddy. And its value is low for the smallest larger eddy, and its value is high for the smallest eddy. And here slope is there for inertial range, and it is always minus 5/3. This slope is always minus 5/3. This slope is always fixed. Please note that. Then method of turbulent flow investigation. There are some experimental technique or numerical technique. This is the experimental technique, which is divided based on the point velocity measurement. It's called Peter tube, which was on potential flow theory, but it doesn't capture the fluctuation. Then we start who is going. Then we continue this lecture. Those who have missed, they can watch after sharing the videos. This is the thermokinetic energy spectrum. Total energy of turbulent flow is equal to energy possessed all fluctuating eddy. It also called turbulent kinetic energy. It's also called fluctuating energy possessed by fluctuating motion. Whatever energy possessed by the fluctuating motion, here that is called thermokinetic energy. You plot the thermokinetic with respect to the wave number, which is equal to the reciprocal of the size of eddy. Then we get this type of flow. This largest eddy is here, which has more energy. A smallest eddy has the lowest energy, and there is the transfer of energy from largest eddy to the smallest eddy. The smallest eddy is called as the Kolmogorov eddy, which has the number is equal to 1, and it transfer thermokinetic energy into the heat by friction. And here slope of the curve for inertial eddy remains constant. It's called as minus 5/3. And the slope of the here this curve for the large eddy depend on the boundary condition. Kolmogorov scale will be depend on the viscosity of the fluid and dissipation rate. And smallest eddy size of small eddy increases with increasing the size of Reynolds number. Here method of turbulent flow investigation. There are some experimental technique or numerical approach. There are some point velocity measure like Peter tube, which is used to find out average flow. Then there is a hot wire anemometry. It is most popular to find out the fluctuating velocity. There is also Doppler velocimetry particle image velocimetry. Here we're focusing on numerical approach. There are some Reynolds average Navier equation are solved, and there are some Eddy rolling simulation. Eddy means we can get fluctuate velocity time scale for fluctuating matter. But in RAS model, we solve average equation based on modeling. And Reynolds average Navier equation can be first moment, second moment. We are not going much detail. The bridging method, this is a research level, people do it. There is a large Eddy simulation. This is also used in academia. And the large Eddy simulation has some subgrade model that we see next slide. Direct numerical simulation used in academia, research only. And here only RAS model are used in industry. And that can use using laptop for the commercial problem. Here is the flow of the backstep. Instantaneous flow, we can see the here fluctuation in the flow. We can see that this fluctuation in the flow, but if we take time average flow, then we don't see the fluctuation. Here we can see the time average flow velocity here. Here is the instantaneous velocity. Instantaneous we can see fluctuation, but if we take time average, the information of instantaneous loss. Just we can see time average, because most of the engineering design we use time average value for design point of view. Is in industry who are interested only in average quantity, but those who want to more physics, they can go to the instantaneous quantity. Here I am covering first technique, laser Doppler velocimetry. CFD point we are not detailing much. Here those who are interested, they can go internet or book, they can study. Here we are interested, this is one technique that is used to find out the velocity based on experiment. Here is the velocity v is there, which is a normal to the laser beam. This is the beams are there and normal to this velocity is there vz, and this velocity vz we can find out as a function of the Doppler frequency. Here is a velocity vz is the frequency of Doppler frequency. Based on that we can find out the velocity. Then there is a laser Doppler velocimetry for jet impingement. Here two laser beams are there and perpendicular this jet velocity is there. That point of view, this orientation should be done. I am not going detail. We are interested only CFD, but just I am presenting in brief. Particle image velocimetry is there, which is popular in academia, also in research. Particle image velocimetry is whole flow field technique providing instantaneous velocity vector measurement in cross section of flow. This technique is being non-intrusive, that means we are not disturbing, and it can be used for the medium speed flow. Here laser gun is there, that passes through the mirror, and then it creates a laser sheet. This is a laser sheet is there, laser light sheet, to visualize the flow. But how can visualize flow? We have to seed the flow with the particle. Here is the flow is there. Then we can add the particle. Then we can add the particle in the flow so that we can see this particle motion in laser sheet. Using this laser sheet, we can find out the displacement of the fluid flow. And please note that this particle light, it has a negligible density and it doesn't affect the flow. By noting the instantaneous location of particle at t and t dash, then we can find out the velocity. Velocity is equal to distance traveled by particle divided by time. By using it, we can find out instantaneous velocity. Once we know the instantaneous velocity, then we can do statistical analysis. There are also limitation of particle velocimetry. It cannot be used for the very large image, large particle, and there is also need for the interpolation of the two images. This is the one image is there, and this is the second image is there, and to interconnect, there should be smooth variation, and particles should be light, and that should not be affect the flow. That's fair to note down. Then hot air monitoring. This is the interesting technique. We have put some probe inside the flow, and this technique is very useful to find out the high speed turbulent flow, and it captures the fluctuation up to 1 megahertz frequency. That means fluctuation up to 1 megahertz that is possible using the this hot wire anemometer technique. Here I discuss brief principle of the hot wire anemometer. Here constant temperature and ammeter is placed in the flow. If flow is passing through over it, it plays across it. This velocity is normal to this probe. This probe, it has prongs are there, this wire, and above it velocity component is perpendicular. And due to velocity, this voltage current is changed, and that is used to find out velocity. And this signal passes through this anemometer, then analog digital converter, then computer, and then your computer display. We can see this velocity fluctuation. We can see the velocity fluctuation are very high, and that high frequency fluctuation can be captured by using hot ion monitor, and that is not possible by using particle image velocimetry or Doppler velocimetry. Next important topic is the statistical analysis of turbulent flow. You plot the instantaneous velocity variation with respect to time, and after it you can see the fluctuation, and then you take this average of the time. It's called a U bar, this average value, and you can find out the fluctuation above or below of this curve. This mean velocity is equal to average of is equal to sum of velocity divided by total time. This is the total time t is there for which averaging is carried out. If data is very high, then we can find out summation of all velocity component divided by total number of data. Here is the number of sample taken for period t. Fluctuating velocity is equal to instantaneous velocity minus average velocity, and then you get fluctuating velocity. Then cross correlation or Reynolds stress per mass. Then we can take product of the fluctuating velocity u dash. Similarly, you can take v dash and integrate over the time. Then you get average value of the turbulent stress. Similarly, we can find the turbulent heat flux like u dash or t dash temperature. Similarly, we can also count the mass flux for turbulent flow or any scalar quantity. That's possible in experiment, and this value can compare with CFD simulation to validate the turbulence model. Here, numerical approach I presented briefly. RANS model is there, large Eddy simulation and DNS is there. Hybrid model is there to reduce the cost of the large Eddy simulation. In DNS, all skills are resolved. There is a 0% modeling. In RANS, there is a 100% modeling is there. In alias, there is 80 to 90% resolution there. There only 10% modeling is there. For hybrid, uh, near the wall flow is modeled and away from the flow is resolved. That there may be 20 to 30% modeling is carried out. RANS, it has a low computational cost and DNS is very high cost. And LES has cost less than the DNS. RANS has a very low cost, hence it is used for the industry application. You see that spectrum of turbulent kinetic energy. In DNS, all EDs are resolved, smallest ED as well as larger ED as well as smaller ED. But LES, only up to this, only the bigger EDs are resolved in using mesh. But the smaller ED, these are the model. These EDs are model. In RANS, all the EDs are model. Large ED has more energy. It transfers energy to the smaller ED, then smaller, then very smaller, and then smaller ED dissipated into the emit energy. Here I am presenting DNA study. This is the DNA study I am going to present. It's carried out by the NASA and Stanford Research University. In this case, very small domain is taken in Z direction. We want to flow in XY plane, and this is the time average boundary layer is there. But DNS all we can get resolution at small level. Here right side I have shown this is the time average velocity profile. Please note that. And this wall region we can see next layer slide. Near the wall, due to viscosity, flow is a streamline. Away from the wall, EDs are significant. And we can see this is a DNS simulation of laminar boundary layer. And here this is the boundary layer. This is age of the boundary layer. It is a time average. Please note this is not instantaneous value. And this is the laminar region. This is a transition region. In transition, we can see the more some fluctuation in turbulent flow. Then we can see the large size of turbulent and more fluctuation. And here we can see the 3D picture of the turbulent boundary layer. This is a turbulent flow. Turbulent flow is the highest level of the EDs. And this is the transition region is there. But here is the isotropic turbulence is there. That means turbulent structure is the same. That means same turbulent structure is observed everywhere. This is called as the isotropic turbulence. Here is the DNS or two-phase flow. You can see the this is the large EDs are there. More fluctuation are there here there. And this simulation is carried out one of the biggest supercomputer. Hence, large ED simulation of complex flow is not possible in industry. Only those academic institutes which have very good supercomputer, they can do direct numerical simulation or large ED simulation. Here I have compared DNS and LES and RANS with respect to time. RANS, here time average is carried out. We won't capture fluctuation. In LES, we can see some fluctuation. We can see this fluctuation. We can capture some level. But in DNS expand, we can in expand we can capture the smallest level of fluctuation. The smallest level of the fluctuation can be captured by DNS and expand. Expand are DNS which are ideal. LES there is a slight approximation. RANS is totally based on approximation, but RANS is less expensive. Here I compare RANS, LES and DNS. RANS is time average. Is a time average based equation is solved. It can be 2D or 3D, but large ED simulation DNS we are solving a steady flow for with considering 3D flow. And the cost for the RANS is 1, that means 1 rupees. Then the cost for the LES will be 100 rupees. That means 100 times cost, because more resolution, more hardware, more data, more time for the analysis. DNS east cost is high because we are resolving all the EDs without approximation. Its cost is very high and it needs supercomputer. Here I shown some presentation, some contour. Once we do time averaging, DNS some EDs are we can see in fluctuation. DNS all EDs are resolved. Here see what is the computational cost. This RANS has a less computational cost compared to the DNS because DNS cost is very high. Alias is intermediate between the alias and DNS. As the number of grid increases, then DNS become highly expensive. Turbulent flow structure is already discussed in the first lecture. This average velocity is equal to sum of the velocity instantaneous velocity divided by time period of the averaging. At any point, instantaneous velocity is equal to average velocity plus fluctuating velocity. Please note that average of fluctuation is equal to 0 because uh, you take a sum of the fluctuation value, there will be some positive value above average value, there will be some negative value. You take sum of the positive negative value, then average of fluctuating quantity becomes 0. Please note that RMS of square of fluctuation and days averaging is not 0 because positive average of positive fluctuation and its square is always positive, but you take negative value of fluctuation and it takes square, it is positive. Uh, hence fluctuating average of fluctuating square is not be 0. Then after it, we can find out thermokinetic energy is equal to half of the square of fluctuating kinetic energy in x, y, z direction. This is the x direction, this is y, and this is the z direction. You put all instantaneous quantity is equal to the average quantity plus fluctuating for the pressure, velocity. Uh, in instantaneous uh, uh, mass conservation equation or continuity equation, then we take average of whole equation. Similarly, put in momentum equation this value, then we take average of whole equation, then we get the average equation. In continuity equation we get this way, in x momentum we get this equation, y momentum we get this equation, and this way. And there is the additional term is there on the right side. This is called as a Reynolds average. This is called as a Reynolds trace. These additional 9 components are there in x, y, z. This is called a Reynolds trace. It can be written as 2ij into second order tensor because it has 9 components and it has it has diagonal element called normal trace and off diagonal called shear trace. There can be similarity between both sides of diagonal element, and then that means there are 9 components are there. Sorry, there are 6 components we can say. That means there are 10 unknown. That means 3 velocity and 1 pressure and 6 Reynolds trace. That means total 4 unknown. To calculate 10 unknown, we have to solve 10 equation. You can write Reynolds Averaged equation in compact form, in index form. This is the additional term is called Reynolds trace that we are going to model. This Reynolds trace is a second order tensor. It has 9 components. In short form, it can be written as this. Matrix form, we can write this way. There are 6 unknown are there. We are considering that this diagonal element are same. This way we can find out the we have to find out 6 unknown. Reynolds states there are 6 unknown. Then we can find out Eddy viscosity model considering the linear variation between the uh, Reynolds space and velocity gradient. There can be non-linear variation. There are non-linear model are there. There can be Reynolds space model are there. The Reynolds space must be resolved so that we can solve momentum equation. Then first approach is to solve all the equations. To solve all the 6 equations separately, then we get this closure. That means once we solve this equation, we can find average quantity. Then this Reynolds model is highly expensive. Then we go to the modeling. This is called a turbulent Eddy viscosity model. According to this theory, Bose hypothesis is applied. According to Bose hypothesis, this Reynolds stress is called anisotropic part of the stress tensor. This is directly proportional to the strain tensor or velocity gradient. Because this part is there, this part was on the left side. You take minus, it become anesthetic part, and this anesthetic part is directly proportional to the strain rate tensor, and that strain tensor we can say the velocity gradient, because mean strain rate tensor is a sum of the velocity gradient. That means this anesthetic part is directly proportional to the mean velocity gradient. In short, it is directly proportional to the mean velocity gradient. And that constant is new term, and is called as a turbulent viscosity. And that once this is model, then we can find out the Reynolds stress. And this term becomes 0, and only K is their thermokinetic energy. Similar to laminar viscosity, turbo viscosity is a flow property. It is not fluid property. Turbo viscosity divided by density, it becomes velocity meter per second. If dynamic viscosity unit has a Pascal per second, similarly turbulent Eddy viscosity unit is the same. Please note down this viscosity. This turbulent viscosity can be homogeneous or non-homogeneous depending on the flow. And to find out this, we are going to find out. Then there are some guidelines for defining the Eddy viscosity. It should be in unit meter per second, and it should be dependent on the velocity and length and time scale, and should be follow velocity variation. And this what viscosity find out numerically, that should be considered with exponent variation. That means all velocity profile near the wall that should be follow similar to the exponent, because this is artificial viscosity, and that is calculated based on model. Modeling means we are approximating the actual flow, and numerically it is should be easy to find out. There are some Eddy viscosity model: mixing length model, small R model, standard case flow model, RNG model, realizable model, case flow model. But in this lecture, we are emphasizing on the standard and case flow model, and these are popular in CFD solver. Case flow model is popular in industry. Here, thermokinetic energy equation is solved. Then mean kinetic energy, thermokinetic energy, total kinetic energy. Mean kinetic energy equal to the half of sum of square of the average quantity. Thermokinetic energy half of average of fluctuating quantity, and total kinetic energy equal to mean kinetic energy plus fluctuating energy. And whatever total kinetic energy that is dissipated into viscous dissipation, and that term is called as epsilon. And we have to note down the unit of the epsilon is equal to k divided by time. Its unit is equal to k divided by time. Please note. And this turbulent viscosity directly proportional to the velocity and length scale. Velocity scale can be determined based on the thermokinetic energy is the square root of the k, and length scale is equal to k raised to power 3 by 2 dr by epsilon. By knowing this, then we can find out the turbulent viscosity. Please note down k unit is a meter per second square because because we consider per unit mass. Its unit of epsilon is a meter square second cube. Uh, Before going to solving case by equation, please note down some length scale. That means size of the geometry. Velocity scale is the square root of the k. Time scale is equal to length scale divided by the square root of the k. And its unit is a second. Thermokinetic energy that we discussed already. Epsilon has unit meter per second cube. Here important quantity is the thermokinetic energy. That is equal to fluctuating velocity divided by average velocity. That is called as the turbulent intensity. It is expressed in terms of the percentage. It can be 0 to generally 30% that thermokinetic that intensity is observed in flow. Not too much. That means that 5% is average value, 10% to 30% is very high value. And that turbo intensity and length scale that we give input to the CFD solver. For standard case plan, we are solving the case plan equation. Its equation is similar to momentum equation. There is a substantial derivative, sum of the unsteady and advection term. Then there is a diffusion part or diffusion part due to viscosity or turbulent. This is a production term and dissipation term. This is a strain rate tensor, magnitude of the strain rate tensor. There is a epsilon transport equation. That means dissipation of thermokinetic energy. Equation is similar. There is inverse time scale. After solving this equation by considering model constant as per experiment, then we can find out the turbulent viscosity. By putting this value k and epsilon and model constant and viscosity of the fluid, we can get this turbulent viscosity. Please note that we can find out turbulent viscosity. Once we know the turbulent viscosity, then put in Reynolds Averaged Navier equation. You put Reynolds Averaged equation or average momentum equation VW. Then we couple with momentum equation, you get average velocity. After getting average velocity, that means we can get we can find out the mean flow. Similar to K square, there is also K omega model. Only second equation is changed for the omega. Omega is epsilon divided by thermokinetic energy, and each unit is the per second reciprocal of the time. K square model equation, a two equation model. Reynolds stress is equal to the minus rho into ui average of the this stress. Say minus rho into ui dash uj dash into this average. And this is the stress tensor, this is the viscosity, and this is the anisotropic part. And here turbo viscosity is equal to alpha into rho into k upon omega. This is the turbo viscosity for k omega model. And here we are solving equation for k and omega. Equation is quite similar here, and the model constant will be different for this model. This is the advantage of k omega model is lower in number computation. We can find out near the boundary layer. Near the boundary layer, we can find out this fluctuation. Please note down. Lower number fluctuation can be found out within statistic k omega model. That is the advantage of the statistic k omega model, and this is the default model in ISS trend. This k omega model must perform better than k square model because it takes care of the boundary layer near the wall. And static k omega model, and in this k omega is all near the wall, and k square model is all away from the wall. You can see the velocity profile will be very smooth, and to capture it, very near was not very smooth velocity gradient, then this K omega model take care of it. Please note that this mesh should be sufficient fine to capture it. Hence, aesthetic omega model is one of the popular model for the CFD modeling flow of the complex problem. There are many types of the RAS model are there. One equation model, two equation model, case-plan family, K omega family, and case-plan. There are standard model, reliable model, RNG model is also there. For K omega model, the existing row K omega model is popular. There is also 4 equation model is available. I don't know whether it is available in ICFluent, but in old version it was available to capture the boundary layer of the jet impingement. When jet is falling on the high velocity, then we can capture this velocity profile correctly by this model. And most of one and two equation model is based on isotropic turbulent assumption. Isotropic means turbulent structure is same everywhere. For non-acidic turbulence, that means turbulent structure is different. Each model has some assumption, advantage and disadvantage, but acidic model is much popular for fully turbulent region. It also in advanced pressure gradient it performs very well. For RAS and LES same is there. RAS we saw time average equation. In LES we saw the filtered Navier equation. These are filtered velocity component. And whatever with filtered equation we calculate this value over the mesh. And those EDs are smaller than this mesh size. Then this flow is resolved using the subgrid model. This is called subgrid model. The difference between RAS and LES is the same, only the difference between viscosity. RAS we are solving the turbo viscosity, here is for subgrid viscosity. Please note, RAS doesn't resolve full flow. We are calculating only average velocity quantity every year. But in LES, we are solving fluctuating quantity or filtered quantity over the mesh. The next is the resolution of turbulent boundary layer. Is a resolution at high speed is important. Turbulent flow has 3 major layers: viscous sublayer, buffer layer, which is away from the viscous layer, then turbulent region. In turbulent region, these EDs are very significant. Near the viscous layer, viscosity effect is dominant, and the EDs are not EDs we won't see. In laminar flow, this is totally dominated by the viscosity, and transition, it is a combination between laminar turbulent flow. Next important thing is near wall regeneration of the turbulent boundary layer. How it is calculated? You have to find out velocity, friction velocity is the square root of the wall shear stress divided by density. You get friction velocity. By using, we can find a non-dimensional velocity is equal to local velocity divided by friction velocity. Then we have to find out the non-dimensional coordinate y plus is equal to wall normal distance divided by friction velocity divided by kinematic viscosity. Wall normal distance, that means the distance of the first layer from the wall. You calculate u plus versus y plus. Then we get this is a viscous sublayer near to wall, and then we get buffer layer where both viscous and inertia force are significant partly, but in inertia sublayer only viscous inertia force are dominant, and that layer is called a logarithmic layer. That mu plus is a function of the ln y plus. For viscous slab layer, there is a linear relation between u plus and y plus. And it is important to capture the this time average velocity using the turbulence model. To capture it, we have to require very fine mesh. We see we have required very fine mesh, so that this very steep velocity gradient can be captured. Please note that this should be captured. For viscous sublayer, this is y plus should be less than 10 or less than 5 is recommended. 10 to 30 for buffer layer and y plus is at 30 to between 30 to 300. This is viscous sublayer. This is called as log layer. In order to save this computational cost for this all these things, then we can use the scalable wall function, because most of the cost for simulation is taken by this high uh, uh, density mesh near the wall. To reduce this, we can use this scalable wall function. By scalable function, that means you can use this u plus is equal to y plus, or u plus is equal to 1 upon k into ln y plus plus constant, so that we can save this cost. This is a comparison of bond, velocity profile for DNS, LES, LES, DNS, and away from the wall you can see the bigger eddy, then smaller, then the smallest eddy near the wall. RAS all eddies are resolved, but in LES these eddies are difficult to some eddies are modeled by the subscript model and large eddy are modeled LES. In RAS all scale are modeled. This all whatever eddy are modeled. Please note that. And if you have any question regarding turbulence modeling, you can visit on the slide, and this lecture will be shared to all the participants. If you have any question,